Good morning, everyone. On Wednesday, I introduced you the magnetic bond. I hope you still remember. And then we moved the topic to semiconductor. So this is the summary of the magnetic bond. In the very beginning, we talk about the quantum theory of solid. The quantum theory of solid is different from the quantum theory of gas. I hope you remember. So we put all the atoms together. I mean very together, and then they become a big crystal. It might be 1 mole of the atoms of the copper. So this kind of phenomena will be different from you discuss the quantum mechanics in gas phase, which is the only discuss the interaction between the 2 atoms or something like this. And then we find out there's a kind of theory which is we call band theory of solid. So we have a band. The band actually is the collection of the energy state. Okay, energy state. So the band gap between the band is very small in terms of the metal. But if you have thousands and thousands band together and they are very close, if you have thousands or thousands of the energy states get together and they are very close, it becomes a band. This is called band. Okay. And then between the band there is a gap. That's what we call band gap. Okay, the energy between the band we call band gap energy. Okay. Right. So this is the band theory of a solid. And then after that, we talk about the bonding energy. So the bonding energy of the magnetic bond are very different. It's from 0.7 electron volt to 88.8 electron volt. It depends on different type of the metals. Okay. And then also we introduce the properties of the metal. Metal has a very good electrical conductivity. Metal has a very high heat capacity and a very good thermal conductivity. And the metal, especially crystal and well-packed metal, is a high reflectivity. Okay, it's flat. And metal, because of glue-like electron cloud or glue-like electron sea, somehow we call this. That's why they have very good ductility. Right, this is metal. And after that, we introduce you the semiconductor. Right, semiconductor, we talk about band gap, and then we have band, and then between the band is called band gap. And after that, we talk about the band gap engineering. Remember? Okay, we can determine what kind of band gap we want, and we can design materials. Okay, so this is very different. This is band gap engineering, and one of the important example I show you on Wednesday is the LED, right? The blue light emitting diode. Right. So today we are going to talk about excitation of the semiconductor. You know, as I just told you that the semiconductor has a band gap between the valence band and the conduction band. So in order to pump electron from the valence band to the conduction band, it requires energy. Okay, if you pump the electron from here to here, and electron in the conduction band can be regarded as a free electron. So you change the conductivity, electrical conductivity. So that's why we call excitation of the semiconductor. And here we introduce you 3 methods. The first method is called photon excitation. We use light to hit this metal, to hit this semiconductor, and to pump the electron from the valence band and to let it jump to the conduction band. This is called photon excitation, the first one. The second one is called thermal excitation. Instead of light, we use thermal energy. we increase the temperature to let this electron jump from the valence band to the conduction band. Okay, the third method is called chemo excitation, which involves chemical. We put different elements into this semiconductor, and which involve chemical reaction. So that's why we use chemo excitation to this is the energy chemical reaction to change the property of the semiconductor. Right. Okay. So now let's move to the first topic, which is photon excitation. Photon excitation. So you know the light is kind of energy. We call it electron magnetic radiation, right? So photon excitation, the first thing we want to know is that if you have a semiconductor and you don't know the band gap of this semiconductor, then how do you find out the band gap of this semiconductor? For example, this is aluminum oxide, Al2O3. Okay, this is aluminum oxide, and it's transparent. I hope you still remember this. And then you want to know the energy, the band gap of this semiconductor of this aluminum oxide. How can you do this? We use photon excitation to find out the band gap of this material. How? Okay, so this has a band gap, right? This has a band gap, right? And then you just use different light to hit beam light. You use different light to hit this material. For example, you change different wavelengths from the red light, which is a very low energy, high wavelength. Remember, and to the blue light, to the green light, blue light, ultraviolet, X-ray might be. Okay, so this energy is incident energy, which is very you change, and then you will see. Okay, so you do this, and then this is the x-axis is lambda. Lambda is the energy of the photon. I just told you can change the different wavelengths. Right, this from small to high wavelengths, so the energy will be small, increase from the right to the left, right? Okay, so this instant photon wavelength, or you can regard this as an instant energy. Okay, so you start to change from weak energy and then to the high energy, and you will find out something, because this has a band gap. If you use the weak, if you use the wavelength which is short, which is a long wavelength, that is the low energy, and this energy is not good enough to pump this electron from the valence band to the conduction band. Then what happens? The energy will pass through this material, right? There is no absorption, so there is no interaction between this material and this light. So this light will pass through, and that's why we can see this is transparent. That's why we can see letters behind this metal material, right? Because the light passes through. Okay, and then you increase and increase, and finally you will find out something very interesting. So once this is the absorption of the instant radiation of this material. Okay, so you decrease the wavelength of this light, and then there is no absorption, because the energy of this wavelength, the wavelength of this light is not enough, or the energy of this wavelength. Let me restart. The energy of this light is not high enough to pump the electron from valence band to the conduction band. That means the band gap is larger than the energy of this light. And this from 0, this is from 100%. So you got a curve like this. You got a curve like this. Why? Because no absorption, no absorption, no absorption, no absorption, until up to this point. And then the energy of this photon was 100% absorbed by this material. Why? Because this instant energy is smaller than band gap energy. However, at this point, this energy, instant energy, is equal to this energy. So you can pump the electron from the valence band to the conduction band. And what happened? This is transparent, transparent. And what happened to this? So this absorption age, which is lambda. Okay, so the energy of this instant photon match the energy of the band gap of this material. And this is opaque. Why? Because all the light have absorbed on these materials. So it become like this. You cannot see the laser behind this material. And you realize, wow, something happened. So this is the lambda, this is the wavelength you need to find out, because this is the band gap. Because the energy in this point match the energy of the band gap. Okay, so how do you find out the energy of this? So the absorption age of a semiconductor, the photon excitation of the electron from the valence band and the conduction band and the emission. So the valence band, you pump, the instant energy is vary, right? So until one point, which is the instant energy larger than the band gap. So the energy larger than band gap. So you have an electron here, and electron will jump from the valence band to the conduction band, and that's why it become opaque, right? So this absorption here. And then when a semiconductor absorbs a light, a particle-like entity called exciton. So exciton actually is a pair of the electron and electron hole. So this is a pair, electron hole. So this is what we call exciton. Okay, and it's a bound state. So this is a pair. Okay, but unfortunately, for this, if you don't have external force, this electron will return back to the valence band because of Coulombic attraction. Of course, you have more electrons here, right? So you have Coulombic attraction, and this is called exciton emission. So once you have magnetic electron radiation, this can follow what? This can follow this equation, which is Planck-Einstein equation, right? So this is the band gap equal to what? This is the energy which is the match to the band gap, which is equal to h, the Planck constant, times speed of light divided by what? The wavelength of this band gap. Sorry, the wavelength of this energy. Okay. So, for example, if the lambda here is 1125 nanometer, so how do you determine the band gap? You know that, right? Do you know? I hope you still remember. This is what I want to ask you. If the lambda is 1125 nanometer, so the band, you put this here, right? You know the constant of Planck constant, and you know the speed of light, so you can get this energy, which is 1.1 electron volt. Remember what is the band gap what kind of material has the band gap of 1.1 electron volt? Which one? Silicon, right? Silicon. Right. So that's why you need to this the photon excitation let you know how to find out the band gap of the material. So exciton emission, there are some explanation for you, and please read this by yourself. So if you have two materials, which is silicon and diamond, these are all sp3 hybridization, right? This is carbon, this is silicon. So you will get different profiles of these figures. But the important thing is you need to find out absorption age. and you can determine the band gap. So for the silicon, the band gap is 1.1. I hope you still remember. The diamond is 5.4, right? So the lambda, as you can use, if you know the band gap of this, so you know the lambda, right? The same, okay? And nanometer. So you can find out this infrared. So this is infrared. So when you use infrared to hit this material, this silicon wafer is opaque, right? So when you use the this is the UV light, which is 229. This is UV light. So that's why in this environment, which you only can see the visible light, right? So all the visible light will pass through this diamond. There's no absorption. So that's why the diamond is transparent. Okay, but all the visible light will be absorbed by this silicon wafer. So it looks like opaque, right? At this environment. However, if you use UV light, the energy is the wavelength is smaller than 229 nanometer. This diamond will become opaque because all the energy will be absorbed by this diamond. Okay, so opaque and transparent. Okay, so when you see something transparent, you know when you see something transparent, you will realize this is the band gap. This is the band gap is larger than what? It's larger than like 3.1 electron volt. Okay. Right. This is first topic. The second topic is thermal excitation. Thermal excitation. How do you use thermal energy? How do you increase the temperature to pump electrons from valence band to the conduction band? Okay, this is thermal excitation. Again, you have a band gap and you have few electrons. This is empty valence band, conduction band, right? Okay, and then you increase temperature in this environment of this material. So if the thermal energy is larger than the band gap energy, again this electron will jump from the from the valence band to the conduction band. Okay, and then this electron carries electrons in the conduction band. Okay, we also this, I hope you remember, this is called exciton, right? It's a kind of a pair of the electron and the electron hole. But this is also called carrier. Carrier can be electron or electron hole. Okay, and you have an electron hole here. So the carrier for this in the valence band is electron hole. And you understand, because this is a pair, so numbers of the electron will be equal to the numbers of the electron hole. Okay. So when the energy, the thermal energy is larger than the band gap energy, a promotion of thermally generated two carriers. Okay. So you need to increase the temperature and to let the thermal energy larger than the band gap energy. So you might ask, Professor, how high the temperature I need to use in order to pump the electron from the valence band to the conduction band? I tell you an idea. At room temperature, the energy of the thermal energy is about 1/40 electron volt. 1/40 for, and do you remember the band gap of the silicon? What's the energy of band gap? What's the energy? 1.1, right? 1.1 electron volt. So will room temperature high enough to pump electron from the valence band to the conduction band? No. It's too little, right? Too little. 1/40, 1 out of 40 electron volt. And this is 1.1 electron volt. Not enough. So you need to increase the temperature. To what level? 100 Celsius, 500 Celsius, 800 Celsius. 1,000, 2,000? Which one? You need to do calculation, or you need to do an experiment, right? Okay, so apply, and then once you have good enough temperature, the temperature is high enough, this electron will jump to here. And at this moment, if you have a potential, which is you apply electrical field between the both end of the wire, then this electron will deliver from the negative side to the positive side. That's why we call the electrical conductivity, right? Okay, so the electron will go from the positive end to the negative end. To the negative end to the positive end. Electron hole will go to the negative end from the positive end. Okay, electron hole will like, positive like negative, negative like positive. Okay, so this is what we call electricity. Okay, now so let's find out the temperature. What's the what temperature can make the electron jump from the valence band to the conduction band using silicon wafer? Okay, but before we talk about this, there's something we need to define first, or there are some stories we need to tell you. I need to tell you first. This is the first one. Is called electrical conductivity. This electron conductivity is the equation of electron conductivity is like this. It's a summation of Ni, absolute value of the Qi and the mu I. What are they? Okay, so electrical conductivity, we use sigma here, and then Ni is the carrier. Remember the carrier, it can be hole, electrical hole, or it can be electron. Okay, electron hole or electron. So this is kind of carrier. And Qi is the charge of the unit carriers. So in this case, the unit carrier is 1, right? The 1, only 1. Okay. Mu is the mobility of the carrier. Mobility of carrier is how the ease with which the carrier can move through the crystals. So it depends on different type of semiconductor. The mobility will be different. Okay, you might mobility means that how fast, how good you can move, right? Okay, so the sigma will be equal to the summation of the carriers times absolute value of the charge times the mobility. I don't need you to remember this, but what I want to tell you, the story is like you will find out in the following pages. Okay, so the mobility will be equal to the velocity of the carrier, the speed, right? And also E is the electrical field. If you have an strong electrical field, okay, and then the difference from the velocity of the carrier. So this is the the equation for you to understand. And then because you have a pair of the you have an exciton, right? So you have carriers, two type of carrier. The one carrier is electron, one carrier is electron hole. So you can split this equation like this too. And because I just told you that the numbers of the electron will be equal to the numbers of the electron hole. So this one and this one is the same. So you can take this out. And the charge of the electron and electron hole are the same, right? So you can take these two out and to make it become like this. No problem. Okay, and then now is that the numbers of the carriers is equal to this. This is an exponential function. Okay, T represent temperature. These are A is prefect. A is a prefector, so you don't need to worry about this. T is represent the temperature. Exponential function EG is the band gap. So bingo, you understand that band gap is related to the numbers of the carriers. Okay, and KB is Boltzmann constant, and T is represent the temperature. So ladies and gentlemen, in the future, once you see the Boltzmann constant times temperature, that means what? Thermal energy. Okay, So actually, when you see this, Eg is called bonding energy, right? Okay, and then this Kb is thermal energy. So actually, in this case, and 2 is represented because we have 2 carriers. Okay, 2 here. Okay. So when you see this, this is what we think the bonding energy is against thermal energy. Okay. So if you have a higher thermal energy, and then you can pump the electron from valence band to the conduction band. So bonding energy against thermal energy. Bonding energy against thermal energy. And this is important. So let's take a look of the electrical conductivity of the copper and silicon. You know, copper is a conductor. Silicon is a semiconductor. So of course the electrical conductivity of the copper must be much higher than the electrical conductivity of the silicon. But once we know this, I want you to know what's the degree of these differences. Okay, you want to know the numbers. So as we know, this is the conductivity, the equation of the conductivity, right? And then N is like this. So at room temperature, the carriers of the electrons for the silicon is 1.3 times 10 to 10 carriers per cubic centimeter. Okay, so that's what we made. That's why I measure. So the conductivity, so the numbers of the carriers for copper is about 10 to 23rd carriers per cubic centimeter. Okay, so once you make a ratio of this silicon and copper, you will realize the ratio of this the ratio of the carriers for the copper and silicon is about 6.5 times 10 to 12. Okay, so this is a huge differences for the carriers. Okay, so when you see these elements for the copper and silicon, you know that the sigma for the conductivity for copper is 5.9 times 10 to 7th, and silicon is 4.4 times 10 to 4th, minus 4th. So again, once you want to see the ratio of these two, the ratio of the conductivity for the copper and silicon, you know the differences is 10 to 11th. So there's a huge difference in terms of electrical conductivity. And then there's also a huge difference between the carrier, the number of the carriers. So, but these two are very close. So now you realize the key factors for this electrical conductivity is this one. It's the numbers of the carriers, not mobility of the electron or mobility of the holes, or not the charge of the electron, the charge of the carriers. This is a key to determine the electrical conductivity. Okay? So the important is how much carriers you put in this material, semiconductor. So very close. These two are very close. So other considerations is a little bit minor only. Okay? They are not too much difference. Okay, so for example, the band gap of silicon is 1.1 electron volt. So for the room temperature is 1 out of 40, right? So you need to increase the temperature. That's why you can excite the electrons from the valence band to the conduction band. And the key is increase the numbers of the carrier, right? In order to have a very good conductivity for the semiconductor. So now you know the key factors for increasing the conductivity is to excite the electron from the valence band to the conduction band, not the mobility of this, not the charge of the carrier. Right, so important is temperature, the increasing of the temperature. But again, before we talk about what's the temperature required to let the semiconductor, to let the silicon become a conductor, we need to introduce a kind of distribution. And there are two types of distribution. Okay, the first one is called Gaussian distribution. Normally, we also call this normal distribution. So what is normal distribution? So normal distribution is a continuous probability distribution in probability theory. So for example, like if we have an exam, like midterm exam, the good exam, the profile will be the good exam for the students will be like this. This is the grade is you have 0 point, you have 100 point, and this is the number of students, right? So the good exam will be like this. So this is number of the student, and this is from like 30 point to 90 points. And normally, majority of the student will have about, let's say, 70, for example. Okay, 75. Okay, but some of the students got 95 points. Some of the students got 10 points for your midterm exam. And this is what we call Gaussian distribution, which we call normal distribution, which looks the same, right? However, so this is what we call bell curve, or we call bell curve. Right, but if we normalize, so this represents a number, right? If we normalize the numbers of the student here, okay, this is total number of the student. Okay, this is the student who got the 70% or 30%, 40% like this. So you normalize, this will be 1, right? This will be 1. So it doesn't matter you have 200 students or 1,000 students take exam. You normalize this. So this becomes 0 and 1. So now you have a ratio here. Ratio. Okay, this is what we call Gaussian distribution. So you have normally the average we call G over bar. Here, this is the average, right? And you have, remember this standard deviation, right? G over bar plus 1 standard deviation plus 2 standard deviation, and or G over bar minus 1 standard deviation. Okay, and the summation of this area is equal to 1 as you normalize this y-axis. Okay, but if you have 3 dimension, you can draw a picture like this. Right, this is called Gaussian distribution. Right, so how about thermal energy, the distribution of thermal energy? Imagine in this room, the temperature is 25, right? For example, now the temperature is about 25 Celsius. However, some places like here, because I'm an energetic person, so the temperature surround me will be higher, like 30, for example. Okay, and that place nobody stay there. The temperature might be 20. So the average temperature in this room is 25. So what's the distribution of the temperature in this environment? It's followed by Boltzmann distribution. It's not Gaussian distribution, it's Boltzmann distribution. The Boltzmann distribution looks like this. So for example, this silicon, if we have a piece of silicon wafer, this is the energy, right? Again, this is energy. You can regard this as a grade, right? The 0, 10 point, 0 point, 10 point, 100 point, something like that. This is the energy. And this is the number of the molecule. When you talk about temperature, that means that the molecular vibration of the temperature, the molecular represent if you put all the molecule together in this room, and it will become the average of the temperature in this room. So this number of the molecules, the energy, okay, is kind of function of energy. So again, you normalize this. This is the total molecules or total species in this environment. So that means you normalize this this factor. Okay, that will be 0 and 1, right? So for the silicon at room temperature, this is silicon, right? The temperature is about 300 Kelvin. 300 Kelvin, which is room temperature, the profile looks like this. The temperature profile looks like this. Okay, I should say the energy profile looks like this. T1. So this is not bell shape. It's called whale shape. 金鱼 whale shape. Whale shape. Okay, before that's a bell, right? Okay, this, and you got a maximum here. However, the average, I'm sure, is not here. The average of the temperature is not here. So this is what we call E over bar. It's a function of T1. So when we talk about 300 Kelvin, that means room temperature, we are talking about this line. However, some molecules has temperature in this area, energy has this area, some energy in this area. Okay? So this is 1 out of 40, which is about 0.025 electron volt. And I'm sure you understand this is the temperature is not good enough to make the electrons from the valence band to the conduction band. Okay? This energy is too low. So energy will be higher than this. So you need to find out what's the ratio of the energy and then what's the number of the molecules which has high enough energy to make the electron to jump from the valence band to the conduction band. And let's say 1.1 electron volt is here. When you think of 1.1 electron volt, the temperature is more than 1100 Celsius. Okay, so this is enough energy for thermal excitation. The temperature is 1100. Okay, and you need to calculate the amount of this, the ratio of these molecules compared to all of this, right? So if the numbers of this electron, numbers of the element, numbers of the molecules are high enough, then this semiconductor can become this silicon can change from a semiconductor to become the conductor. So you need to find out fraction. The equation to represent this fraction is this. The fraction is the function of temperature. Okay, and then from 1.1 electron volt, and you accumulate to infinite, and it's the n. It's a function of E here and the n, and divided by it's kind of you have summation from E here. That's for sure, right? That's for sure, and it's equal to this E exponential function, which is band gap energy minus band gap energy divided by Boltzmann constant times temperature. Remember this? This is the bonding energy against thermal energy. Okay, so I don't want to do some more calculation for you, but after calculation, this ratio is about 10 to minus 19. What does that mean? If we have 10 to 19 molecules, there's only one electron or one molecule has the ability to pump electron from the valence band to the conduction band, and this is very little. 10 to minus 19, the ratio of this is very, very little. So the room temperature is not good enough. So you need to start to increase the temperature. So silicon at room temperature is not conductive because the ratio of this amount, the ratio is too little. Okay? So you increase the temperature, let's say because the melting temperature is 16.87 Kelvin, which is about 1414. Okay, 1414 Celsius. Okay, so this is the T2 here. And because 1100 is good enough, so you need to calculate the amount of these molecules or elements and compare to this one. So you start to do this, and you realize the ratio of T2 divided by T1 is about 5.6. What does that mean? This means that the function of T2 to T1 will be increased dramatically. So if you increase the temperature by 5.6 times, the carriers will increase about 10 to 15, this number. That's increased a lot. So that's why when you increase to the 1687 Kelvin, this material become conductive. Silicon become conductive. Okay? But unfortunately, once you increase the temperature like this is not solid silicon. This is a liquid silicon or glass-like silicon. So you cannot use this anymore because this becomes a molten silicon. It changes the shape. Okay? So that's why for the thermal energy, it's not easy to change the property of the semiconductor in terms of the electrical conductivity. Okay? So the molecular dynamics, we talk about temperature. If you increase the temperature, according to the Boltzmann distribution, you will increase the ratios in this part. Okay? So not only increase the temperature, but different elements or different gases, they have different distribution. The shape is different. Okay? Right. The next topic I'm going to talk is very important, which we call chemical excitation. Because when you use photon excitation, we understand the band gap. Okay? But the photon is not easy to, it's not easy to, once you want to change the property of the materials, you need to use the light, which is not easy to use. But once you want, and then the second one is thermal excitation. You want to change the property of the semiconductor, you need to increase the temperature. But unfortunately, temperature is too high, so the shapes of the material will change, or the property of the physical property of the material will be changed. So it's not good. So finally, the scientists and engineer, they find out that, well, why don't we use chemical excitation to change the property of the semiconductor? Okay, this is the topic we are going to talk. But before I talk about this topic, let's pray. So now we are going to talk about thermal excitation. Thermal excitation. The thermal excitation here is that, well, instead of using photon or using thermal energy, we try to change we just try to put some elements into this semiconductor. This is a sp3 hybridization of silicon. You can regard this atom as a silicon or carbon. But if you put this silicon here, that will be silicon, right? So the band gap in this case will be 1.1 electron volt. So the thermal excitation is the carrier injection. We replace this silicon atom to let it become another type of atom by introducing impurities in silicon. So the impurity of this silicon is 11 nines. Okay, 11 nines. So 99.999999999%, which is very, very pure. However, we want to change the purity of this. We replace this atom to become group 4, group 5A or group 3A. For example, this is what we call dopants. Dopants. You have some dopants. Dopants is good. When we call the impurity as a dopant, is good. But when we call impurity as a contaminants, which is not good. For example, if you put hydrogen in here, this is not good for silicon. But if you put the boron in this silicon, this is good. We call dopant. Okay, so impurity is good or it cannot be good. For example, if you eat a portion of rice, okay, you put a sesame, 芝麻 on your sesame, it tastes good, right? So this sesame is impurity. Okay, 你如果吃饭你放那个 sesame 芝麻，对不对？ It tastes good. However, if you put 小强, that's not good, right? So 小强 is contaminates. Sesame is dopant. when you regard this as a portion of rice. Okay? Disgusting. I'm sorry about this. I hope you are not eating at this moment. Okay. Right. So dopant is not changing the composition of the materials. So this is what we call engineered material. This very pure, which is not easy to make. However, you put these different things into this design, into this pure materials, and you change the property. Again, this is engineering, right? Okay. Via chemical change. Okay. So you tailored composition to give a target properties. You can change the amount of this impurity. So they provide you different you change the different change the amount of this impurity that provide you different properties in terms of electricity, right? Electrical conductivity. So there are two types of the impurity here we want to use. The first one is boron. Boron is electron consumption. You know, boron has 3 valence electrons. Silicon has a 4 valence electron in the outermost shell. So boron has 3, so boron lack of 1 electrons. Okay, compared to the silicon. And if you put arsenic into the silicon, this is there are 5 electrons. So you have 1 more electrons, which is we call electron donor or electron donation. Okay, so you change this to boron or arsenic. Right. So first of all, let's take a look at this case. Arsenic dope silicon and its donor energy band. So once you have silicon here, and you change the silicon to become arsenic. So once you change the silicon to become arsenic, you have 1 more electron, right? You have 1 more electron somewhere, because you know the valence electron has 4 and arsenic valence electron of arsenic has 5. So you have 1 more electrons. And now the question is, where is this electron? Here, here, here. Okay, and then where's the energy of this? What is the energy of the electron in this place? Because you understand these electrons are all located in the valence band. But where is the energy of this electron? Okay, this is the question. Okay, and we call this extra electron, we call it donor. Donor. Okay, what is the energy of this electron? Again, let's use the simplest way, the Bohr model. For the hydrogen, you have 1 only electrons, and n equal to 1. Energy will be what? Energy will be minus 13.6 electron volt. I'm sure you all remember this number, right? This is the energy of the electron in the hydrogen atom. However, this is not hydrogen, and this is not only 1 single hydrogen. This is a silicon crystal, a lot of silicons. So we modify this equation. We modify silicons because it's solid state. Okay, let's change epsilon. We change to modify epsilon, and then mass we change to effective mass. So after you do the calculation, I'm sure I don't have time to talk about this, and you don't need to know this. So once we use this parameter, we put this parameter into this equation, we realize that the energy of this electron will be minus 0.02 electron volt. Okay, so where is the minus 2 and 2.2 electron volt? This is 1.1 electron volt. So where is minus 2? 0.02 electron volt. It's very, very close, and after we measure, this is calculation, right? Centuries ago. This is calculation of centuries ago, and this is the measure. When we measure the energy of this electron is minus 0.045, which is not too bad. Okay, the measure and the calculation is not too much difference. And where is this 0.045 electron volt? It's somewhere around here. So this electron, the energy of this electron will be here. And now you understand it's about 0.05 electron volt, and this is very easy to jump from this level to here. And you can deliver electricity, you can deliver this electron, right? Okay, so if you have more, so how far and this is the first one, you need to know the energy. So it's very easy to reach the conduction band by this one. So if you have more electrons here, you have better conductivity, right? Okay, so it depends on, but if you have more, and you might change the structure of this silicon. So you cannot have too much. You cannot have too little. Okay? So now we understand the energy. And after that, we want to know where is this electron. So how far does the electron go? So again, let's use the simplest case, which is hydrogen. You know, hydrogen, for the Bohr model, you understand R1 will be 0.35 Armstrong, right? So from this one, if this is hydrogen, this to this will be 0.35 Armstrong. Okay, so this one to this one is 3.5 Armstrong, and then again we multiply the epsilon and the mass, so we got the R donor electron will be 30 Armstrongs. What does that mean, 30? Which is too far, right? This is not, actually it's not here, it's somewhere here already, because the distance between two silicons is about 2.35 Armstrong. And this electron, it will be 30 Armstrongs. That means this is 2.35. So this might be somewhere, you don't know. It's a kind of free electron already. Excuse me. Okay? So actually you can regard this as a very free electrons. You just give a little bit energy. At least electron will become a conductive electron. Right, so now the thermal energy versus the dopant energy is that the more dopants enter the substance, if you have more, and you got more free electrons, right? So you put more electrons here, you got better conductivity. Okay? And then, of course, you need to know the more numbers of the electrons. Because you don't have hole, you don't have a pair, you just have electrons. Okay? So the impurity is, this is much more than holes, right? So electrical properties are essentially loose from the impurities. So basically, you don't need to worry about how to pump the electron from here to here. You just need to think how to pump the electron from this level to here, and how many of these electrons. So this is what we call intrinsic behavior. The property of this semiconductor is dominated by these electrons, not the electron here. Okay, so dopant dependent. So depends on how many dopants. So the undoped silicon inhibit intrinsic behavior. Intrinsic behavior is this one. Okay, behavior, intrinsic behavior, extrinsic behavior. So normally we talk about extrinsic behavior. Okay, and you know the temperature is very low. It's room temperature, so there are only a few electrons can pump to here. You know, 1 out of 10 to 15, I remember, if I remember it right. So the very, very little amount of the electron. So in this case, electron hole is much more than electron. The number of electrons is much more than the electron hole, right? Because there is no electron hole. And this is what we call supervalent dopant. Supervalent dopant. And we call this N-type semiconductor. N stands for negative, because you have a lot of electron, right? So electron, the charge of electron is negative charge. So we call negative type, or we call N-type semiconductor. So you always, for the semiconductor, you always have N-type and P-type. So N-type now you know is negative. So what's the P stand for? P is positive, right? Positive. So now we are going to talk about positive type dopant silicon. So P-type is called positive. So instead of changing the silicon to become arsenic, you change this silicon to become what? Boron. Boron. Okay? And then when you change this silicon to become boron, you miss one electron, right? Because boron has 3 valence electron. And now you miss 1 electron here. So this has a 1 electron hole. Okay? So again, we want to know the energy of this electron hole. Where's the energy of this electron hole? Where is, okay, we don't know. It must be somewhere. Okay? So the hole we call acceptor. Acceptor. And once we calculate, when we do the calculation, the energy of this electron hole is somewhere here. And this is about 0.05 electron volt. And very low. So once you have electron in the valence band of the silicon wafer, and then this electron can jump to here easily, right? Can jump to here easily. So you have electron hole in valence band, and you make this become a conductivity. So this is electron, okay? An electron can jump to here. So the number of the hole, if you change this to boron, so the number of hole will be increased. Okay, so the number of the hole, electron hole, will be much more than the numbers of the electrons. So we call subvalent dopant, not supervalent. It's called subvalent dopant, and this is what we call P-type semiconductor. Okay, so P stands for positive. So, and you know, when we talk about the electricity, before we always talk about electrons. So if the electron jump to the conduction band, it becomes free electron, and you apply a bias between the both end of the wire. So the electron will move. This causes the electrical conductivity, right? Okay, how about the hole? Because you don't have electron, you have a lot of electron hole. So how can we illustrate the hole movement? This is the one. So if you have electron here and you jump to here, or there's an electron hole. So another electron will, this one move to here, and this one might be will be moved, right? Move. So another electron will try to fill in this hole. So the electron here, or electron hole, and the band gap is very low. So it doesn't require a lot of energy. So electron will move from this part to this part. Okay, and for this case, electron move to this part to this part. Okay, you might ask, why, Professor, why this electron will move from this to here? Why electron will move from here to here? Because of bias, right? If you have a positive end and negative end here, the electron will move through the holes. Okay, it causes the electrical conductivity. Okay, so now I want you to have a guess. Electron move faster or hole move faster? As you can see, the hole will move, right? If the electron move from here, you see the whole electron hole move from this to here. So I want to ask you, electron in N-type move faster or hole in P-type move faster? Which one move faster? Electron, right? Why? Because you need to have an electron hole in order to fill let electron to fill. But this is free electron. It can go very easily. Okay, so the p-type and n-type, the differences between these. And we can call this a mobility. Okay, mobility. Right, this is a comparison of the thermal excitation versus the chemical excitation. You know, thermal excitation, you have to pump from valence band to a conduction band. This is called, we call intrinsic property. Okay, and this is what we call extrinsic property, because we really doesn't use the electrons from the valence band to the conduction band. We use a dopant. We use dopant. So there's a acceptor band, which is the hole here. There's a donor band. Okay, this is acceptor band and donor band. Right, so please read this by yourself, and I think that's good enough. So, you know, from semiconductor to become a transistor, this is a great breakthrough. In 1947, you know, because of Taiwan can be very popular, very famous on semiconductors, thanks for this invention, semiconductor to become first transistor. You know, semiconductor is semiconductor, but you have to make it become a device. The first device they use is a single crystal germanium. Okay, so it's only one transistor in 1947, and these three gentlemen got Nobel Prize. They win a Nobel in physics, I think. Okay, they are great. Okay, so this is silicon wafer. So in order, because when you look at this wafer, you don't know this is n-type or p-type. So in the past, not now. Okay, in the past they give you the shapes to tell you, well, this one is what this is. This shape is p-type, and with this angle, if you have angle, if you cut these two edge, that will be 111 orientation. You don't know why it's 111, don't worry. Okay, and this is 100, something like it. So please tell me, what is this silicon wafer? Is that p-type or n-type? Anybody tell me? What's this type? What is this silicon wafer? N-type or p-type? P-type, right? This is the one. And the surface is 111 orientation. Okay. And this is unprocessed silicon wafer. This is processed silicon wafer. You know, you have chips. You have squares here. There are thousands and thousands transistor here. You know how many? 40亿颗电晶体到100亿颗电晶体。Just a little bit like this. And there are so many transistors inside this silicon. Thanks for the great engineers like you. You are my gun in this industry. Forget about what I say, okay? Right, so this is processed silicon wafer. And then when you take this out, okay, this is what we call chip. And then when this is a chip, which is, you can imagine this is 2 centimeter times 2 centimeter chips. And in this chip, you have millions, trillions transistors inside this. And this technology in TSMC probably is 40亿颗, something like this. It's not exactly like this, but you know, this is what we call transistor. The CMOS is combination of PMOS and NMOS. But anyway, you don't need to worry about this. But this one, and when we say the 3 nanometer technology or 5 nanometer technology, we are always talk about the width of this wire. If you get thinner, you get better, you got smaller transistor. If you have small transistor, you can put a lot of transistors into this square, okay, into 2 times 2 centimeter square chips, okay. And the wafer can be 6, 12, 6, 8, 12 inches. And chips is about, you say you can remember, it's about 2 times 2, something like this. So when I was a kid, when I was very small, we used this. We practice using this. This is a capacitor, transistor, and resistor. Okay, so you don't do this now. And you put this become very, very small. That's why we call integrated circuits. This is called discrete circuits. You can use your hand to make a kind of devices. But however, now you have a very small chips, and chips you put it into your motherboard in your computer, right, or in your mobile phone. Okay. Right. This is the innovation of technology. You understand now. These are different shapes. This is the old type. We call planar FET. FET stands for field effect transistor. Okay, FinFET and gate all around. This is the modern technology. And thanks for the engineers like from the engineering college. They make a great effort to make this happen. Okay, so this is the summary of semiconductor. So I think I will stop here. And next topic we are going to talk is how do you make gas, liquid, or solid. Okay. So that's it for today.